This is Scholar Strife doing some math today. In geometry, we're going to be exploring solids. And like any other geometry section, we're going to start off with some vocabulary. A polyhedron is a solid bounded by polygons on all sides. Sorry if my picture doesn't look right, but what I'm trying to do is make a box. So think of a box. Each side is a polygon, and each side is a flat surface called a face. So each side is a face of a polygon, or a polyhedron. An edge would be something like this green line here. It's a line segment formed by the intersection of two faces or a polyhedron. So that would be an edge. Any of, well, think of the edges of a box. Those are the edges. The vertex would be the corners. So like right here, right here, right here. These would be our vertexes. And then what we call the bottom or top of our polyhedrons So here I'm making kind of like a triangular box there. This bottom piece here would be the base, or you can call it the top. There's a little pyramid there. The bottom is the base. A regular polyhedron is a polyhedron whose faces are all regular congruent polygons. That means all the, if you're looking at one particular side, like say it's a square, all the sides are the same, all the angles are the same. And then maybe on another side you have a pentagon. But basically all the sides, or all the polygons are regular. Regular means sides are congruent, angles are congruent. A convex polyhedron is any 2 points on a convex polyhedron can be connected by a line that lies inside or on the polyhedron. All vertices point outward. So basically, if you're connecting all the pieces of the box, or all the corners, all the vertexes, you can draw a line in between them, and it always stays inside the box. It never goes outside. Cross-section. So let me draw a box again. A cross-section is when they take a piece off and kind of focus in. A lot of engineers do this when they have to explain a specific part of a device or a building. Kind of like a zoom in, and they take a piece of it. And then we got Euler's theorem. The number of faces, edges, and vertices for any polyhedron can be found uses Euler's theorem. So F stands for the number of faces, V stands for the number of vertices or corners, and E stands for edges. Faces plus vertices is equal to the number of edges plus 2. Example 1. Tell whether each of the figures shown is a polyhedron. If so, name the polyhedron and tell how many faces, edges, and vertices it has. So this is a polyhedron because it is closed. All the sides are polygons. In this case, they're all triangles. And we have 1, 2, 3, 4 faces. I need more space. 4 faces. Now we count the edges. So I'll use red here. That's 1 edge. 2 edges. 3, 4, 5, 6. So 6 edges. And then looks like 4 vertices. Corner, 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 corner. 4V. So this would be a pyramid. A triangular pyramid. Part B, this is what it would be called as one. So looking at the top here, which is the same as the base, there is 6 sides. So that's a hexagon. This is what it's called, is a hexagonal prism. Prism are like boxes. And then what gives it the hexagonal name is you look at the base, and that's what we name the prism after, is whatever the shape of the base is. This one has 8 faces, 18 edges, and 1, 2, 3, 4, 5, 6, 12 vertices. And then part C, it is not a polyhedron because it has curves. Anything with curves is not a polyhedron. Polygons are not curvy. So anything with curves is not a polyhedron. All right, let's do that again. So this is a pentagonal prism because the base, now it's sitting sideways, but the base is the 2 pentagons. So there's always a top and bottom. So this is a pentagonal prism. So even though it's sitting on the rectangle, that is not the base. So once again, number 2, these circles are the base. But this is not a polyhedra anyways. It is curved. This is 7 faces. Edges is 15. And there's 10 corners. 3, this is a pyramid. And the bottom determines what type of pyramid it is. And the bottom is a rectangle. So it's a rectangular prism. It has 5 faces, so 5 sides, 8 edges, and 5 vertices. So example 2, use Euler's theorem to calculate the number of faces. So we have F plus V equals E plus 2. Wait a minute. They don't give us any information except for the picture, but we can just use the picture to calculate. Well, that's odd. Hopefully we run into an actual example where we can use this formula. But if we count it all up, there are 8 faces and 12 vertices, and there's 18 edges. So if I did this correctly, these would be the same. Okay, describe the shape formed by the intersection of the plane and the solid. So we're basically looking at the shaded, the darker shaded region. Here, let me highlight it, well, with yellow here. So we're talking about this section here. So that is a circle, or an oval, but we'll go with circle. Here we got 1, 2, 3, 4, 5. So that's a pentagon. And then we got a rectangle here. All right. Here we go. Now we can use the formula, Euler's formula. Faces plus vertices plus edges plus 2. Is it possible for a polyhedron to have 16 faces, 34 vertices, and 50 edges? So I'm going to plug all those into my formula here, and I'm going to get 50 equals 50 plus 2. 50 does not equal 52, so no. Alright, number 5, that's a rectangle there, in that dark shaded region, that intersection. And then we got another pentagon for number 6. And, oh, that's different. We got a triangle. Bam, bam, bam. Hopefully this helped you out. Have a good day.